Welcome, dear listener. I'm Tina, scientist and lifelong terrible sleeper. I made AI for sleep to help ease my own restless nights, after I learned a busy mind tends to drift off when it's gently occupied, not forced quiet. So everything here is built to give your thoughts somewhere soft to land. Welcome, dear listener, to this quiet space where we can explore together one of the most pressing questions of our technological age. Tonight, we'll gently examine why nations around the world are pouring billions into building their own artificial intelligence capabilities, driven by promises of sovereignty and independence. Yet beneath the political rhetoric lies a complex web of technical realities that few fully understand. The path to true AI sovereignty demands control over manufacturing processes smaller than viruses, vast computational resources, and talent pipelines that take decades to develop. Let's begin by understanding what this sovereignty actually means in technical terms and why the costs are far greater than most governments realize. But first, a gentle observation. Most of the people who drift off to this channel have never actually hit subscribe. So if I've ever helped you in any way, you can return the favor with a simple and free action that will encourage me to keep going. Now, without further ado, let's fall asleep. When politicians talk about sovereign AI, they paint grand visions of national independence in artificial intelligence. But the technical reality resembles trying to grow a redwood forest when you don't control the soil, the seeds, or even the rain. True AI sovereignty means controlling every layer of an incredibly complex stack, and each layer presents its own unique challenges for any nation trying to break free from global dependencies. Modern AI chips require manufacturing processes at 3 nanometer and 5 nanometer scales, where the features etched into silicon are smaller than most viruses. TSMC in Taiwan controls roughly 60% of the world's most advanced chip production, making them a critical choke point that every AI powerhouse must navigate, though other foundries like Samsung and Intel are working to expand their own advanced capabilities. Think of TSMC as the world's most sophisticated bakery, one that took decades to perfect recipes for the most delicate pastries imaginable. Building a competing foundry isn't just about buying the right ovens. It's about mastering thousands of intricate processes, from the purity of materials to the precision of timing, all while your competitors have a 20-year head start. Even if a country somehow built its own advanced foundries, the next layer up presents fresh dependencies. The actual chip designs, the architectures that make modern AI possible, are dominated by NVIDIA's GPUs and increasingly by custom silicon from companies like Google and OpenAI. These aren't just hardware specifications. They're the accumulated wisdom of thousands of engineer years spent optimizing for the peculiar mathematics of neural networks, particularly the transformer architectures that power large language models. NVIDIA's CUDA software ecosystem creates another sticky layer of dependency. Like a programming language that half the world's developers have learned to speak fluently. Even if you manufacture your own chips, if your software stack can't run the vast library of CUDA-optimized code, you're asking researchers to abandon their existing tools and start over with unfamiliar alternatives. Moving up the stack, we encounter the foundational models themselves, and here the dependencies become more subtle but no less significant. Training a frontier language model requires not just massive computational resources, but enormous datasets scraped from the internet over many years. The most capable models today learned from Common Crawl, Wikipedia, GitHub, and countless other sources that represent a distinctly Western, English-dominated view of human knowledge. As recent studies have shown, these datasets can significantly impact model capabilities across different languages and cultural contexts. This data dependency runs deeper than simple language bias. The internet itself developed along particular cultural and economic lines, with certain types of content overrepresented and others barely visible. A model trained primarily on English text even when translated, carries embedded assumptions about everything from social relationships to technical practices that may not align with other cultural contexts. Then, there's the human feedback component, which has become crucial for making AI systems behave in ways that users find helpful and harmless. The reinforcement learning from human feedback, or RLHF, that shapes models like ChatGPT relies on human annotators making thousands of judgments about which responses are better. These annotators, often based in specific regions and working for particular companies, embed their own cultural values and preferences into the model's behavior. Picture this human feedback process like a massive collaborative sculpture, where thousands of artists each add tiny refinements to shape the final form. But if all your sculptors come from the same art school, trained in the same traditions, the resulting sculpture will reflect those particular aesthetic values, no matter how many individual artists contributed. For a nation seeking AI sovereignty, each of these layers presents a different cost-benefit calculation. Manufacturing advanced semiconductors requires investments measured in tens of billions of dollars and decades of development time. Developing competitive chip architectures demands deep expertise in both hardware design and the evolving needs of AI workloads. Creating software ecosystems means convincing developers to abandon familiar tools for unproven alternatives. The data and human feedback layers offer more realistic paths to differentiation, like tending your own garden rather than trying to recreate an entire agricultural system. A country could prioritize collecting and curating datasets that reflect its own languages, cultures, and knowledge traditions, then use human feedback from its own population to shape model behavior according to local values and preferences. But even this more modest approach faces technical challenges. Smaller language communities may lack the massive text corpora that current training methods seem to require. Human feedback systems need careful design to avoid amplifying the biases of individual annotators. And models trained on more limited datasets may struggle to match the capabilities of systems trained on the full breadth of internet content. Some countries are exploring hybrid approaches, like building on top of existing foundation models while adding their own fine-tuning and feedback layers. This resembles renovating an existing house rather than building from the foundation up, accepting some dependency in exchange for faster deployment and lower costs. The geopolitical reality adds another dimension to these technical choices. Export controls on advanced semiconductors, restrictions on cloud computing access, and limits on research collaboration can force countries towards sovereignty, whether they prefer it or not. What begins as a technical optimization problem becomes a matter of national security, when access to critical technologies can be cut off during political disputes. Understanding these layers helps clarify what's actually possible when politicians promise AI independence. True sovereignty across the entire stack remains extraordinarily difficult and expensive, but meaningful autonomy at specific layers, particularly around data and human feedback, offers more realistic paths forward for countries willing to invest in their own AI capabilities while accepting some continued dependencies in areas where global supply chains remain dominant. We've just seen how the quest for AI sovereignty reveals itself as an intricate challenge, from the nanoscale precision required in chip manufacturing to the concentrated control that TSMC holds over the world's most advanced production. The complexity runs deeper than most realize, touching every layer of the technological stack. Rest here for a moment with this understanding, knowing that each nation's journey toward independence must navigate these fundamental constraints. Now, let's turn our attention to how one country has chosen to respond to this challenge, as Britain made a bold declaration that would reshape its entire approach to artificial intelligence development. A year ago, at London's bustling Tech Week, two leaders made a bold declaration that would reshape how Britain thinks about artificial intelligence, like planting a flag on new territory. Jensen Huang from NVIDIA and UK Prime Minister Keir Starmer announced that the UK would become an AI maker, not an AI taker, a phrase that's become something of a rallying cry across the nation's technology landscape. Think of this commitment like tending a garden, where careful cultivation over months begins to show real growth. Over the past year, that declaration has sprouted into tangible momentum across Britain's infrastructure, from scrappy startups in converted warehouses to enterprise boardrooms in glass towers, all powered by what they're calling sovereign AI deployments. The UK's AI minister, Kanishka Narayan, recently reflected on this progress with evident satisfaction, noting how sovereign compute is now powering British startups to push boundaries in everything from drug discovery to healthcare robotics. It's like watching a country back its own talent with the infrastructure to match, he explained, pointing to NVIDIA's decision to invest billions as validation of what's being built across Britain. The foundation of this transformation rests on compute power. And here the numbers tell a compelling story. Over the past year, the number of AI cloud providers planning to deploy infrastructure on UK soil has doubled, like watching a construction boom unfold across the digital landscape. Nebius, one of NVIDIA's AI cloud ecosystem partners, has announced plans for 3 new deployments of advanced AI infrastructure, continuing to build out its commercial hub in London. When these deployments reach full capacity in 2027, they're expected to consume 65 megawatts of power, enough electricity to run a small city. Meanwhile, CoreWeave is establishing itself within the UK government's designated AI growth zones, while 7 more NVIDIA partners have similar plans in development. BT and Nscale have announced joint plans to build sovereign AI data centers across 3 existing BT sites, combining NVIDIA's infrastructure with Nscale's software stack and BT's nationwide connectivity backbone. At the heart of this sovereign compute story sits Isambard AI, the UK's most powerful computer, like a massive engine humming quietly in the background of Britain's AI ambitions. Built on 5,400 NVIDIA GH200 Grace Hopper superchips and running entirely on zero-carbon electricity, it powers some of the nation's most ambitious AI research projects. The UK government's Sovereign AI Fund acts as the financial catalyst, putting Isambard's capability to work by backing homegrown companies and providing the domestic infrastructure they need to scale their ambitions, much like a venture capitalist with access to the world's most powerful computational resources. Among the fund's first recipients is Ineffable Intelligence, which recently announced a collaboration with NVIDIA to build the future of reinforcement learning infrastructure. 4 other recipients are UK-based startups in NVIDIA's Inception program, each pushing different frontiers of AI research using Isambard's computational muscle. Cosine is building an end-to-end sovereign AI coding platform specifically designed for highly regulated industries like financial services, critical infrastructure, and national security. Using Isambard, they're training a large parameter mixture of experts, multimodal agentic language model that can natively handle data types beyond traditional text and images. Alistair Pullen, Cosine's co-founder and CEO, puts it simply: access to Isambard enables the project. Full stop. He explains that they already have the people, the data, and the training methodology, but this level of compute power was the missing piece, like finally having the right tool for an impossible job. Cursive is tackling a different challenge, building self-improving AI systems that learn continuously from real-world data, enabling autonomous operation over extended periods. They're developing new memory-augmented architectures with dramatically larger context windows, using the Sovereign AI Fund resources and recently adopting NVIDIA's Megatron LM framework for distributed training at scale. Talfin Evans, Cursive's co-founder and CEO, sees the Sovereign AI Fund as more than just processing power, describing it as a statement about investing in UK AI capabilities. He notes that sovereignty has actually become a buying criterion for customers, like a quality seal that opens doors previously closed to international competitors. DoubleWord represents the UK's first dedicated inference lab, optimizing every layer of the AI stack to maximize what they call IQ per dollar, like an efficiency expert fine-tuning a complex manufacturing process. They deploy open models including NVIDIA Nematron 3 Super 120B and build on NVIDIA's Dynamo inference framework. On Isambard, DoubleWord's early results achieved 70 times faster model cold starts, essentially the time it takes to load models into memory, and 4 times lossless KV cache compression. These improvements are critical for long-running agentic workloads, resulting in inference costs that are 90 to 95% lower than other leading providers. Maryam Arek, DoubleWord's co-founder and CEO, emphasizes that sovereign AI creates the most impact at the inference layer, since that's when you actually extract value from the model. She wants that value created in the UK, with UK compute and UK data centers, like keeping the entire supply chain within national borders. Prima Mente takes AI into the realm of biological research, building foundation models to identify new biomarkers, subtypes, and drug targets for Alzheimer's, Parkinson's, and ALS. With their Isambard allocation, they're developing Pleiades 2, a foundation model that combines 5 different biological data modalities into a unified system. Using NVIDIA Blackwell GPUs, Prima Mente has achieved nearly 3 times speedups in model training, while also leveraging NVIDIA Parabricks for genomic data processing and NVIDIA Transformer Engine for model optimization. Hannah Madden, the company's co-founder, explains that research suggests Alzheimer's might actually be 25 different subgroups of disease, like a single umbrella covering many distinct conditions. NVIDIA's £2 billion investment in the UK startup ecosystem, developed in collaboration with leading venture capital firms, is bringing new capital and advanced AI infrastructure to major UK hubs, including London, Oxford, Cambridge, and Manchester, like seeds scattered across fertile ground. UK membership in NVIDIA's Inception program has increased by 50% over the past year, while AI-native companies like DoubleWord, Synthesia, and Poly AI are scaling globally from their UK roots. The NVIDIA Developer Program now includes more than 200,000 UK developers, creating a substantial community of technical talent. The educational component includes collaborations with the UK Department for Science, Innovation and Technology on 6G and AI skills development. The 6G collaboration has established testbeds at 4 UK universities, while NVIDIA's Deep Learning Institute has delivered new courses to participants from over 30 UK universities. The Sovereign AI Forum, which launched last year with 7 charter members, has grown to include dozens of participants across government, industry, and the startup community, functioning like a bridge between policymakers and technical implementers. This forum helps turn abstract policy goals into concrete deployment roadmaps. Enterprise AI applications are moving from experimental pilots to full production deployments across various sectors. Appian is building digital twins of 2 National Health Service hospitals, combining autonomous devices, ground robots, computer vision, and robotic simulation into integrated systems. Deliverance AI helps regulated enterprises run, govern, and scale AI agents within their own environments through a single control plane. building what they call an agentic operating system designed for organizations where data sovereignty is absolutely non-negotiable, like a secure vault that never opens to the outside world. Glass Futures has installed an AI-driven digital twin of its glass furnace, capable of testing and predicting new optimal ways to manufacture glass. This digital twin utilizes NVIDIA accelerated computing and the NVIDIA Physics NeMo framework to simulate complex thermal and chemical processes. One advanced is fine-tuning NVIDIA Nematron 2 Nano 9B using NeMo Auto Model for an AI consultation and triage application, training it with sovereign, real-world NHS primary care patient data. Orbital Industries has announced AI infrastructure that accelerates time to first token, while Reading Football Club is partnering with Stellia to establish an AI Center of Excellence. All of this activity reflects momentous progress in UK AI leadership, like watching a nation methodically build the foundation for technological independence. It offers a glimpse of where this sovereign AI journey is heading, with infrastructure, talent, and ambition finally aligned in service of a single, transformative goal. You've just heard how Britain planted its flag in the AI sovereignty landscape, transforming a bold declaration into tangible momentum across startups and enterprises nationwide. The UK's commitment to becoming an AI maker rather than taker has begun to show real growth, with sovereign compute now powering everything from drug discovery to healthcare robotics. Allow yourself to rest with this image of a nation backing its own talent with matching infrastructure. Next, we'll explore one of the most fascinating technical challenges these sovereign systems must navigate: the complex dance between data protection laws and global computational power. Picture a library with strict rules about which books can leave the building, and you'll understand one of the most fascinating technical challenges facing modern machine learning infrastructure. When you're serving AI models across different regions of the world, especially when European data protection laws come into play, you're essentially managing a complex dance between where your data can legally live, where your computational power sits, and how quickly you can deliver results to users. The General Data Protection Regulation, or GDPR, fundamentally changed how we think about data movement by establishing the principle that European citizens' personal data should generally stay within European borders. Think of it like a medieval city with walls, where certain valuable goods, once inside, cannot be transported beyond the gates without very specific permissions and safeguards. Now, here's where the technical complexity begins to unfold. Modern AI systems, particularly large language models and recommendation engines, often require massive computational resources that might not be evenly distributed across all geographic regions. Your most powerful GPU clusters might be in Virginia, your primary data centers in Ireland, and your users scattered across dozens of countries, each with their own regulatory requirements. The naive approach would be to simply replicate everything everywhere, like having identical workshops in every town. But this becomes prohibitively expensive when you're dealing with models that require hundreds of gigabytes of memory and specialized hardware. Instead, most organizations find themselves needing to architect systems that can intelligently route requests while respecting data residency constraints. Cross-region inference introduces a fundamental tension between performance and compliance. When a user in Berlin makes a request that could be processed by a powerful model sitting in a US data center, the round-trip latency alone might add hundreds of milliseconds to the response time, not counting the additional overhead of ensuring the request itself contains no regulated data. This is where the architecture starts to resemble a sophisticated postal system with multiple sorting facilities. You need request routers that can examine incoming traffic and determine not just where it should go for optimal performance, but where it's legally allowed to go based on the data it contains and the user it's serving. One common pattern involves deploying smaller, more specialized models within EU regions, while keeping larger, more capable models in regions with fewer restrictions. It's like having a local pharmacy that can handle common prescriptions immediately, while more complex cases get referred to a specialized hospital, but only after ensuring all patient privacy requirements are met. The technical implementation often requires sophisticated data classification systems that can analyze requests in real time. These systems need to identify personally identifiable information, determine the legal basis for processing, and route accordingly. Think of it as having an intelligent mail sorter that can read addresses, understand postal regulations, and choose the appropriate delivery method for each piece of mail. Edge computing becomes particularly important in this context, as it allows you to push certain types of processing closer to users, while maintaining compliance boundaries. Rather than sending raw user data across continents, you can perform initial processing locally, extract non-sensitive features or embeddings, and then send only those derived representations to more distant computational resources, an approach that recent research has shown can maintain model performance while significantly reducing privacy exposure. Consider how this works in practice with a recommendation system. A user in Amsterdam might generate behavioral signals that need to be processed to update their recommendations. Instead of sending their entire interaction history to a US-based model, a local edge node might compute anonymized behavioral embeddings that capture the essential patterns without exposing individual actions. The networking layer becomes crucial here, almost like designing a rhetoric system with carefully controlled tributaries. You need dedicated network paths that ensure EU data never accidentally flows through non-EU infrastructure, even during failover scenarios or traffic spikes. This often means maintaining parallel network topologies and implementing strict routing policies. Caching strategies also require careful consideration. Traditional content delivery networks that might cache responses globally need to be configured to respect data boundaries. It's like having a network of local banks, where certain types of deposits can only be stored in vaults within specific jurisdictions, even though the banking software itself might run on shared infrastructure. Model-serving infrastructure needs to be designed with compliance as a first-class concern, not an afterthought. This means implementing features like data lineage tracking, audit logging, and the ability to completely purge specific user data from all systems when required. Every component needs to understand not just what data it's processing, but where that data originated and what legal constraints apply. The challenge extends to model training as well. If you're continuously learning from user interactions, you need to ensure that EU user data used for training stays within compliant infrastructure, while still benefiting from the improved model performance. This often leads to federated learning approaches, when models are trained across distributed data sources without centralizing the raw data, or carefully designed data anonymization pipelines that preserve utility while protecting individual privacy. Load balancing becomes more complex when compliance boundaries are involved. Instead of simply routing traffic to the least loaded server, your load balancers need to understand geographic and legal constraints. It's like managing a fleet of delivery trucks, where certain vehicles are only licensed to operate in specific regions, regardless of how busy other areas might be. Monitoring and observability systems must also respect these boundaries, while still providing comprehensive insights into system performance. You need to track latency, error rates, and resource utilization across regions, while ensuring that logging and metrics collection don't themselves violate data residency requirements, a challenge that has led to new approaches in privacy-preserving system monitoring and distributed telemetry. The result is an architecture that resembles a sophisticated diplomatic network, where information flows according to carefully negotiated protocols and treaties. Each component understands not just its technical role, but its place in a larger compliance framework that spans legal jurisdictions and regulatory regimes. As you drift toward sleep, consider how these systems represent a fascinating evolution in distributed computing, where legal and technical constraints interweave to create new patterns of architecture. The solutions that emerge often prove more robust and thoughtfully designed than systems built with purely technical considerations, creating infrastructure that serves both performance and principle with equal dedication. I'm curious how this one sits with you. Does the idea of where all of this is heading comfort you or quietly unsettle you? Tell me in the comments. I read them on my own sleepless nights. We've just explored how data protection regulations like GDPR create new boundaries in our interconnected world, establishing walls around European citizens' data that fundamentally change how AI systems can operate. The challenge becomes managing this delicate balance between legal compliance and computational efficiency. Let this complexity settle gently in your mind, understanding that these are the real constraints shaping our digital future. Now we'll see how one major cloud provider has engineered an elegant solution to serve AI workloads across multiple regions while respecting these important boundaries. Picture a bustling European marketplace where vendors from different cities work together to serve customers, each specializing in different goods but sharing resources when demand spikes. This captures the essence of how AWS has designed cross-region inference for artificial intelligence workloads across Europe. Cross-region inference, or CRIS as it's commonly known, represents Amazon Bedrock's managed capability for automatically routing AI model requests across multiple AWS regions within predefined geographic boundaries, allowing applications to tap into broader computational capacity while maintaining strict data governance controls. Think of inference profiles as carefully drawn maps that define exactly where your AI requests can travel. These profiles act as the fundamental resource in Amazon Bedrock that specify which regions can serve as destinations for your model inference requests, with routing designed to optimize throughput while minimizing latency overhead. The architecture operates with two key geographical concepts: your source region, which is where you initiate the API request, and destination regions, which are the locations where Amazon Bedrock can actually route and process that request according to the profile's defined boundaries. Global inference profiles work like an international shipping network with no restrictions. They can route your model inference requests to any supported AWS commercial region worldwide, transmitting input prompts to whatever destination offers the best capacity and performance at that moment. During this global routing process, your data travels much like a secure diplomatic pouch. It remains encrypted and never leaves AWS's private network backbone, with the destination region automatically selected to optimize available model capacity and minimize response overhead. The resilience benefits become particularly apparent during peak usage periods, when having access to all available supported regions means your generative AI applications can gracefully handle capacity shortages or regional availability issues that might otherwise cause bottlenecks. Geographic CRIS profiles, by contrast, operate like regional trade agreements with carefully defined boundaries. The EU-specific profiles ensure that when you're working with European data, your requests stay within a controlled set of European Union regions. For EU CRIS specifically, the routing logic follows strict geographical rules. Requests originating from a source region within the EU can only be routed to other AWS regions that also lie within the European Union, creating a contained processing environment. The system handles edge cases thoughtfully. Requests from London can route between available EU regions and London itself, while Zurich requests similarly stay constrained to EU regions plus Zurich, and requests originating outside the EU using EU CRIS will optimize only within EU regions plus their original source region. Security in this cross-region architecture works like a private tunnel system. All AWS to AWS traffic flows traverse AWS-operated backbone paths rather than the public internet, with data encrypted in transit between regions and never exposed to external networks. Consumer applications must explicitly opt into cross-region inference by specifying a CRIS profile ID instead of a plain model ID in their code, giving developers precise control over whether their requests use EU-constrained routing or global routing for each model invocation. Geographic inference profiles maintain static definitions, meaning AWS won't add new regions to existing profiles. If additional destination regions become necessary for EU CRIS, Amazon Bedrock publishes entirely new geographic profiles with fresh inference profile identifiers. Access control integrates seamlessly with AWS Identity and Access Management, functioning like a sophisticated keycard system where administrators can precisely define which applications and users can access different foundation models or CRIS profiles, supporting GDPR's data protection by design principles. Transparency and auditability come through AWS CloudTrail, which acts like a detailed logbook that continuously monitors account activity, capturing metadata from every API call, including model invocations, though not the actual payloads themselves. When examining CloudTrail events, you can see both source and destination regions for each model invocation through the inference region field in the additional event data section, providing clear visibility into where requests were actually processed. Model invocation logging offers an optional deeper level of detail, like having a stenographer record complete conversations. It captures full requests, responses, and metadata, which customers can route to CloudWatch logs or Amazon S3 storage. The logging architecture maintains a centralized approach where all log entries, regardless of which destination region processes the request, get recorded only in the source region where the request originated, streamlining monitoring while respecting local data processing requirements. Customers can discover available CRIS profiles through multiple channels, consulting the official documentation that lists all system-defined profiles, navigating to the cross-region inference section in the AWS console, or programmatically querying through AWS SDKs like Boto 3. Amazon Bedrock operates within the scope of the CISPE Data Protection Code of Conduct, which functions like an official certification that provides independent verification for GDPR compliance. This code was approved by the European Data Protection Board in May 2021 and formally adopted by the CNIL in June. The service maintains rigorous technical and organizational measures to protect data confidentiality, integrity, and availability, regardless of which AWS region processes the requests, while AWS continues updating customers on evolving privacy frameworks, like the EU-US Privacy Shield, through dedicated communication channels. Cross-region inference ultimately provides generative AI applications with both flexibility and compliance options, like having multiple carefully planned routes to reach your destination. You can choose global profiles for maximum resilience or geographic profiles for stricter data locality, depending on your specific regulatory requirements and risk tolerance. You've just discovered how AWS designed their cross-region inference system like a carefully orchestrated marketplace, where AI requests can travel along predefined paths to optimize performance while maintaining strict data governance. The architecture reveals the sophisticated engineering required to balance computational efficiency with regulatory compliance. Rest here with this understanding of how complex these technical solutions truly are. As we continue, we'll shift our focus to examine how these same AI systems are sometimes used in ways their creators never intended, as foreign actors attempt to influence public discourse. Imagine you're watching a chess game where one player keeps moving pieces while wearing a disguise, pretending to be someone else entirely. That's essentially what researchers at OpenAI discovered when they found 2 clusters of ChatGPT accounts, likely originating from China, that were using AI models to generate content designed to influence American debates about artificial intelligence and technology policy. The first operation, which OpenAI dubbed the Data Center Bandwagon Campaign, worked like a gardener planting seeds in someone else's garden, hoping they'd grow unnoticed. These accounts generated social media comments and images claiming that data center build-outs for AI were driving up electricity prices for average American families, attempting to cultivate concern about the infrastructure that powers modern AI systems. The second cluster, named the Tech and Tariffs Campaign, took a different approach, focusing its generated content on criticizing U.S. tariffs as attempts to dominate technological competition. Interestingly, the operators specifically instructed their prompts to exclude China's leader Xi Jinping from the output, while including only President Trump, like a ventriloquist carefully choosing which voice to throw and which to keep silent. This second campaign extended beyond just generating content, connecting to a network of likely inauthentic social media accounts that were also targeting OpenAI directly by claiming that ChatGPT user data had been compromised. These allegations were entirely false, but they represent a broader strategy of attacking the credibility of AI companies themselves. What makes these operations particularly noteworthy isn't their apparent success in shifting public opinion, which researchers found no evidence of, but rather what they reveal about the strategic thinking behind them. Like a locksmith testing different keys on a door, PRC origin influence operators appear to be experimenting with narratives against AI infrastructure, which forms the foundation of U.S. technological leadership and economic growth. The approach these operators took follows a well-established playbook, much like how invasive plants often take root by mimicking native species. Foreign influence operations have long sought to latch on to existing local issues and sincerely held beliefs, using them to build credibility, amplify divisions, or exacerbate public distrust, rather than creating entirely new controversies from scratch. In this particular case, the operators attempted to covertly insert themselves into ongoing American debates about the future of the country's AI capabilities, while carefully concealing their true identity and motivations. They exploited genuine public concerns about energy prices and the local impacts of data center development, topics that already had some traction in affected communities. The researchers found no evidence that these influence operations achieved meaningful breakout beyond their own activity, suggesting that the campaigns remained largely contained within their artificial networks, rather than spreading organically through genuine social media users and communities. OpenAI's decision to publish these findings serves multiple purposes, functioning like a lighthouse, warning ships of hidden rocks beneath the surface. By sharing this intelligence, they aim to help the broader technology industry, governments, civil society organizations, and the general public better identify and disrupt similar attempts by foreign threat actors to manipulate legitimate public debates. The broader context here involves what researchers describe as efforts to weaken democratic institutions and advance what they term totalitarianism with AI characteristics, referring to the use of artificial intelligence for surveillance, censorship, and control over political, social, and private life. These influence operations represent a new frontier in information warfare, where AI tools themselves become both the weapon and the target, like a blacksmith's hammer being used to forge chains rather than useful tools. The same generative AI capabilities that can help people solve complex problems and create valuable content can also be weaponized to generate misleading narratives at scale. The sophistication of these campaigns lies not in their technical complexity, but in their strategic targeting of specific policy debates that matter for America's technological future. Rather than broad, scattershot disinformation, these operations focus precisely on issues that could potentially slow or complicate the development of AI infrastructure in the United States. For the technology community, these discoveries highlight the importance of monitoring how AI systems are being used and by whom. Much like park rangers keeping watch for signs of poaching or other illegal activities, the ability to detect and analyze these influence operations depends on having robust systems in place to identify suspicious patterns of usage across large user bases. As AI capabilities continue to advance and become more accessible, the potential for similar influence operations will likely grow, requiring ongoing vigilance from both technology companies and the broader security community. The challenge lies in maintaining the openness and accessibility that make AI tools valuable, while preventing their misuse for covert influence campaigns that undermine democratic discourse and decision-making processes.
We've just witnessed how AI systems can be weaponized for influence operations, with actors using ChatGPT to generate content aimed at shaping American debates about technology infrastructure and policy. These campaigns reveal the hidden ways that sovereign AI capabilities can be turned toward geopolitical ends. Let this sobering reality rest with you gently, understanding that technology's power can flow in unexpected directions. Now we'll explore how the global community is responding with new transparency measures as organizations work to help people distinguish between human and AI-generated content. Picture a bustling marketplace where vendors are creating beautiful artwork, crafts, and written pieces using new, powerful tools. But the shoppers walking through can't quite tell which items were made by human hands and which were crafted by these remarkable new instruments. This is the digital world we're living in today, where artificial intelligence has become a sophisticated craftsman, helping people create and edit content in ways we've never seen before. And as these AI tools grow more capable and widespread, people deserve to know the origins of what they encounter online. The European Commission recently published something called the Code of Practice on Transparency of AI-generated content. And OpenAI has stepped forward to support this initiative, recognizing it as a crucial building block in implementing the broader EU AI Act and creating a more transparent digital ecosystem. Think of this code like a set of community guidelines for a neighborhood. Everyone agrees to follow certain practices so the whole area becomes more trustworthy and pleasant to live in. OpenAI's commitment here isn't a sudden decision, but rather the natural continuation of years of internal research,
Product development, and collaboration with the broader technology community to strengthen what experts call provenance for AI-generated content. Since 2024, they've been adding something called C2PA metadata to their DALL-E 3 image generation tool, like attaching a detailed birth certificate to every digital image that explains exactly how and where it came into existence.
This European initiative represents just one part of OpenAI's broader approach to AI governance in the region, and in 2025, they became the first U.S. company to sign the EU's General-Purpose AI Code of Practice, reflecting their belief that clear, workable rules can help artificial intelligence develop responsibly while giving companies the certainty they need to continue innovating. It's like having traffic laws that everyone understands and follows. The roads become safer for everyone, and drivers know exactly what's expected of them. The fundamental reason provenance matters becomes clearer when you consider that AI tools are increasingly becoming part of how people build, imagine, and share their ideas with the world. People need to understand where content comes from so they can interpret it with confidence. Much like how knowing whether a book is fiction or nonfiction helps you approach the text with the right mindset and expectations. Provenance signals work by giving people context about content's source, explaining how it was created or edited, and helping verify whether something is actually what it claims to be. Beyond individual understanding, provenance also helps protect the broader digital ecosystem by making it easier to detect disinformation campaigns and support election integrity, creating a kind of immune system for the internet. The most effective provenance methods need to be built collectively and work seamlessly across the entire ecosystem, which is why OpenAI collaborates with coalitions like C2PA, bringing together news organizations, device manufacturers, online platforms, and AI providers to advance interoperable standards. Think of this like different manufacturers agreeing on a universal charging port. When everyone uses the same standard, the technology works better for everyone involved. C2PA metadata serves as an important foundation for provenance, helping content carry information about its origins, creation process, and the entities that have verified this information. However, metadata isn't foolproof. It can be stripped away, lost during uploads and downloads, or broken by common transformations like file format changes, resizing, or even something as simple as taking a screenshot. To make provenance more resilient against these challenges, OpenAI takes what they call a multi-layered approach, combining different signals, product safeguards, and collaboration across the wider ecosystem. It's like building a fortress with multiple walls, moats, and watchtowers. If one defense fails, the others are still there to protect what's inside. Their current implementation includes C2PA content credentials for images, which they began adding to images created and edited by DALL-E 3 in ChatGPT and the OpenAI API, and they've continued expanding these provenance signals across all OpenAI-generated images. Each image essentially carries a digital passport that travels with it, documenting its journey and origins. For additional robustness, images generated with ChatGPT and the OpenAI API include both C2PA metadata and SynthID watermarks, creating a redundant system where metadata can carry richer information while watermarking helps preserve a signal even when the content moves through different contexts and platforms. Think of this like having both a visible price tag and an embedded security chip in a valuable item. Each serves a slightly different purpose, but together they provide stronger protection. OpenAI has also created a public verification experience at openai.com/verify, where people can check whether supported images contain provenance signals associated with OpenAI-generated content, functioning like a public authentication service, where anyone can verify the origins of digital content they encounter. Beyond their own products, OpenAI joined the C2PA Steering Committee in 2024, participating in this cross-industry effort that involves software companies, camera manufacturers, media organizations, and online platforms working together to establish universal standards. This collaborative approach resembles how different industries might work together to establish safety standards for something that affects everyone, like food packaging or building codes. Provenance technology works alongside other product safeguards, complementing policies, classifiers, reporting channels, and enforcement processes that reduce deceptive uses of AI-generated content, including likeness misuse and election-related deception. These multiple layers of protection work together like the various security measures in a bank: cameras, alarms, guards, and vaults, all serving different but complementary functions. While provenance shows tremendous promise, it remains a nascent field with significant practical challenges. As signals can be lost when content moves through the complex pathways of the internet, metadata gets removed, watermarks degrade over time, and labels only help in the specific places where people actually encounter the content. The development of more reliable, robust, and interoperable provenance techniques still requires substantial work and cooperation among all the different players in the ecosystem, much like how building a comprehensive public transportation system requires coordination between city planners, engineers, funding agencies, and the communities that will use the services. The Code of Practice sets an appropriately ambitious direction for advancing provenance techniques. But as it gets implemented in the real world, it needs to stay grounded in methods that actually work in practice, while remaining flexible enough to acknowledge and work around the limitations of current technology. Looking ahead, OpenAI has committed to continuing their work on strengthening content transparency across their products, contributing to the development of interoperable standards, and improving verification tools, while working collaboratively with the AI Office, member states, and the broader AI community to build a safer, more transparent artificial intelligence ecosystem that serves everyone's interests. Someone else is awake right now, listening to this very moment with you. If that's you, leave a word below, so the rest of us know we're not alone at this hour. You've just learned how the European Commission is working with companies like OpenAI to create new standards for transparency in AI-generated content, building community guidelines for our digital neighborhood. This represents a crucial step toward helping people understand the origins of what they encounter online. Allow yourself to breathe with this knowledge that thoughtful frameworks are being developed to address these challenges. Next, we'll journey back to explore one of the foundational innovations that enables AI to learn while keeping personal data safe and local. Back in 2016, a team of researchers at Google introduced a groundbreaking approach to machine learning that would reshape how we think about training models on personal devices, proposing a method they called federated learning that keeps sensitive user data local while still enabling the benefits of collaborative model training. Like a neighborhood book club where members discuss insights without sharing their personal journals, this approach allowed mobile devices to contribute to model improvement without ever uploading their raw data to central servers. The core insight was elegant in its simplicity. Instead of moving data to where the computation happens, they moved the computation to where the data lives, having each device train locally and share only the learned improvements. The motivation for this work stemmed from the recognition that modern smartphones and tablets had become repositories of incredibly rich personal data, photos, text messages, voice recordings, location patterns that could dramatically improve machine learning models if it could be safely utilized. Rather than a traditional mining operation that extracts raw materials to process elsewhere, federated learning resembled a network of local refineries, each processing materials on site and sharing only the refined products. The researchers identified key applications like improving phone keyboards through better language models trained on actual typing patterns, or enhancing photo organization by learning from real user behavior, all while maintaining privacy by design. Their proposed algorithm, federated averaging, or FedAv, worked through an iterative process where a central server coordinated training rounds across participating devices, selecting a random subset of clients each round to perform local training steps before averaging their model updates. Think of it as a distributed orchestra where musicians practice individually between rehearsals, then come together periodically to synchronize and blend their improved techniques into a unified performance. Each device would receive the current global model, train it further on local data for several epochs, then send back only the updated model parameters, which the server would combine through weighted averaging based on each client's dataset size. The researchers conducted extensive experiments across multiple architectures and datasets to validate their approach, testing everything from simple neural networks to convolutional networks on MNIST digit recognition and recurrent networks on a Shakespeare text corpus divided by character roles. Like a botanist testing seeds across different soil conditions. They systematically varied key parameters: the fraction of clients participating each round, C, the number of local training epochs, E, and the local batch size, B. Their most striking finding was that FedAv could reduce communication rounds by 10 to 100 times compared to traditional synchronized stochastic gradient descent, while often achieving better final accuracy. One of their most important discoveries was how robust the algorithm proved to be under non-IID data distributions, where each client's data looked dramatically different from the overall population, a critical property for real-world federated learning, where individual users have highly personalized data patterns. They created pathological test cases for MNIST, where clients had data from only 2-digit classes, simulating extreme data skew, yet FedAverage still provided substantial communication savings over baseline approaches. This was like proving that a recipe could work even when different kitchens had access to completely different sets of ingredients, with the final dish still turning out well when techniques were properly combined. The communication efficiency gains came primarily from increasing computation at each client between communication rounds, rather than simply adding more parallel clients to each round. By having devices perform multiple local SGD steps, controlled by parameter E, on smaller mini-batches, controlled by parameter B, before model averaging, they found sweet spots where a CNN model could reach 99% accuracy on MNIST in just 18 communication rounds compared to 626 rounds for the federated SGD baseline. It resembled a relay race where runners could cover much longer distances between handoffs, dramatically reducing the total number of exchanges needed to complete the course. Their experiments on the Shakespeare dataset proved particularly illuminating for real-world applications, as they partitioned the text by character roles in plays, creating a naturally unbalanced and non-IID distribution that closely mimicked how user data would actually be distributed across devices. Counterintuitively, they found this realistic data distribution was actually easier for FedAverage to handle than artificially balanced IID data, achieving up to 95 times communication reduction compared to 13 times for the balanced case. This suggested that the natural clustering and variation in real user data might actually be beneficial for federated learning, like discovering that a patchwork quilt's irregular patterns actually made it stronger than uniform fabric. The research also revealed important insights about model averaging in neural networks, showing through careful experiments that averaging model parameters could work surprisingly well when models started from the same initialization, even when trained on completely different data subsets. Their visualizations of loss landscapes when interpolating between two separately trained models demonstrated that shared initialization created a kind of connected pathway through parameter space. This was akin to two hikers starting from the same base camp and exploring different mountain trails. Despite taking different routes, they remained in regions where their paths could be meaningfully combined. However, the researchers also discovered limits to local computation, finding that excessive local training, very large E-values, could sometimes cause the algorithm to plateau or even diverge, particularly in later stages of training. They observed this behavior most clearly in the Shakespeare language modeling task, where training for too many local epochs between averaging steps led to diminishing returns. Like a pendulum that swings too far in one direction, the algorithm needed careful tuning to balance local computation with global coordination, suggesting that adaptive approaches might decay local computation as training progressed. The implications of this 2016 work extended far beyond the specific technical contributions, laying groundwork for what would become a major paradigm shift in machine learning toward privacy-preserving collaborative training. The paper demonstrated that federated learning could work across diverse model architectures, multi-layer perceptrons, convolutional networks, and LSTMs, suggesting broad applicability across different domains and use cases. Like planting seeds that would grow into an entire forest ecosystem, this research established fundamental principles that would later flourish into production systems serving billions of users while keeping their personal data private and secure. We've just discovered the elegant simplicity of federated learning, where computation travels to data rather than the reverse, allowing devices to collaborate like members of a book club sharing insights without revealing personal details. This breakthrough from Google researchers opened new possibilities for privacy-preserving machine learning. Rest with this beautiful concept for a moment, appreciating how innovation can protect privacy while enabling progress. Now we'll delve deeper into the technical challenges that make federated learning so complex, examining why distributed AI systems require fundamentally different approaches. Back in 2019, researchers at Carnegie Mellon University and other institutions published a comprehensive survey that would help define the emerging field of federated learning, examining how to train machine learning models across distributed devices without centralizing the data. Like a library system where books never leave their home branches, but knowledge is still shared across the entire network, federated learning allows smartphones, hospitals, and IoT devices to collaboratively improve AI models while keeping their sensitive data local. The authors identified 4 core challenges that make federated learning fundamentally different from traditional distributed machine learning: expensive communication, systems heterogeneity, statistical heterogeneity, and privacy concerns. The communication challenge in federated networks stems from the fact that transmitting data can be orders of magnitude slower than local computation, particularly when dealing with millions of participating devices like smartphones. Much like a postal system where sending letters across continents takes days, while local deliveries happen in hours, federated learning must minimize the frequency and size of messages exchanged between devices and central servers. The paper outlined 2 primary strategies: reducing the total number of communication rounds or compressing the size of transmitted model updates at each round. Systems heterogeneity presents another fundamental challenge, as devices in federated networks vary dramatically in their computational power, memory, network connectivity, and battery life. Like an orchestra where some musicians play on vintage instruments while others use modern equipment, the federated learning system must accommodate everything from high-end smartphones with 5G connections to older devices running on 3G networks. The authors noted that typically only a small fraction of devices participate at any given time, perhaps hundreds out of millions, and devices frequently drop out due to connectivity or power constraints. The third challenge, statistical heterogeneity, arises because data generated across different devices is rarely identically distributed, violating fundamental assumptions used in traditional distributed optimization. Picture a garden where each plot has different soil conditions and grows different plants. Each smartphone user has unique texting patterns. Each hospital serves different patient populations, and each autonomous vehicle encounters different traffic scenarios. This heterogeneity means that a single global model may not serve all devices equally well, leading researchers to explore personalized models and multitask learning approaches. Privacy concerns complete the quartet of core challenges, as even sharing model updates instead of raw data can inadvertently reveal sensitive information about users or organizations. The situation resembles a detective story, where seemingly innocuous clues can be pieced together to reveal secrets. Gradient information and model parameters can potentially be reverse engineered to extract private details about the training data. The authors noted that while techniques like differential privacy and secure multi-party computation offer some protection, they often come at the cost of reduced model performance or system efficiency. To address communication efficiency, The paper discussed three main approaches: local updating methods, compression schemes, and decentralized training. Local updating methods, exemplified by federated averaging, FedAverage, allow devices to perform multiple gradient descent steps locally before communicating with the server, like students working independently on homework problems before sharing their final answers with the teacher. FedAverage became the de facto standard for federated learning, despite lacking convergence guarantees and sometimes diverging when data is highly heterogeneous across devices. Model compression schemes offer another path to communication efficiency by reducing the size of transmitted messages through techniques like sparsification, quantization, and structured encoding. These methods work like a skilled artist who can capture the essence of a complex scene with just a few strategic brushstrokes, preserving the most important information while discarding redundant details. However, the paper noted that classical compression techniques from data center environments cannot be directly applied to federated settings due to challenges like low device participation and the potential staleness of accumulated errors. The system's heterogeneity challenge spawned research into asynchronous communication, active device sampling, and fault tolerance mechanisms. Traditional asynchronous methods that work well in data centers become problematic in federated settings where delays can stretch from hours to days or be completely unbounded. Like a clockmaker trying to synchronize timepieces that run at wildly different speeds, federated learning systems must accommodate extreme variability in device capabilities and availability while maintaining algorithmic correctness. Active device sampling emerged as a strategy to intelligently select which devices participate in each training round, considering both systems' resources and data quality. Rather than passively accepting whatever devices happen to be available, this approach resembles a casting director carefully choosing actors for different scenes based on their availability, talent, and fit for the role. However, the authors noted that most proposed methods assumed static device characteristics and couldn't adapt to real-time fluctuations in computation and communication delays. Statistical heterogeneity in federated learning drew inspiration from established fields like multitask learning and meta-learning, but required new approaches to handle the scale and constraints of federated networks. The MoCA framework, for example, allowed devices to learn separate but related models while sharing a common representation, like musicians in different bands who share fundamental music theory but develop their own unique styles. However, such methods often struggled to scale to massive networks or were restricted to convex optimization problems. The paper also highlighted fairness concerns that arise when training on heterogeneous federated data, noting that naive approaches might bias models toward devices with more data or commonly occurring device types. This resembles a voting system, where some constituencies might be systematically underrepresented if proper weighting mechanisms aren't employed. Several proposed solutions included QFFL, which gives higher weight to devices with higher loss, and agnostic federated learning, which uses minimax optimization to handle any mixture of client distributions. Convergence analysis for federated learning proved particularly challenging because traditional parallel SGD analyses rely on identical data distributions across workers, an assumption that rarely holds in federated settings. Like trying to predict the weather by assuming all regions have identical climates, classical theoretical guarantees break down when each device represents a fundamentally different data-generating process. The FedProx method emerged as one solution, making small modifications to FedAverage to ensure convergence in heterogeneous settings, while maintaining practical applicability. Privacy-preserving techniques for federated learning included differential privacy, secure multi-party computation, and various cryptographic approaches, though each came with significant trade-offs. These methods operate like a sophisticated encoding system that allows meaningful collaboration while protecting sensitive details, but the computational and communication overhead often proves substantial. The authors emphasized that understanding and optimizing these privacy utility trade-offs remained a considerable challenge for practical deployment.
The survey also touched on decentralized training topologies as alternatives to the standard star network architecture, where devices communicate only with neighbors rather than a central server. This approach resembles a relay race where information passes from runner to runner rather than all runners reporting to a central coordinator.
While potentially reducing communication bottlenecks, decentralized methods faced limitations in federated settings, with existing work restricted to linear models or requiring full device participation.
Fault tolerance mechanisms became critical in federated learning due to the high likelihood of device dropouts during training, leading to both practical strategies like simply ignoring failed devices and more sophisticated approaches like coded computation. The challenge resembles directing a flash mob where participants might disappear at any moment. The choreography must continue smoothly despite unpredictable absences. However, simply ignoring dropouts can introduce bias if failed devices have specific data characteristics, such as those from areas with poor network connectivity. The authors identified several promising future directions, noting that federated learning sits at the intersection of multiple research communities, including machine learning, distributed systems, security, and privacy. Like a river formed by the confluence of multiple streams, the field requires expertise from diverse areas to address its multifaceted challenges. They emphasize that while individual components like compression or privacy techniques exist, integrating them into cohesive, practical systems remains an open challenge. This 2019 survey proved prescient in identifying the key challenges that would shape federated learning research in subsequent years, providing a foundational framework that researchers still reference today. The work recognized that federated learning represents more than just distributed machine learning with communication constraints. It constitutes a fundamentally new paradigm requiring novel approaches to optimization, systems design, and privacy preservation. Like a compass pointing toward uncharted territory, this survey helped orient the research community toward the most promising and challenging directions in collaborative machine learning. You've just explored the 4 core challenges that make federated learning fundamentally different from traditional approaches: expensive communication, systems heterogeneity, statistical heterogeneity, and privacy concerns. These constraints shape every aspect of how distributed AI systems must be designed and operated. Let these technical realities settle gently, understanding the complexity that lies beneath seemingly simple concepts. Finally, we'll examine how hardware itself must evolve to meet these challenges, as Google's latest supercomputer architecture reveals the infrastructure required for tomorrow's AI systems. Back in 2023, Google's research team unveiled their TPU v4 architecture, a fascinating evolution in their domain-specific supercomputing approach that represented their 5th-generation design and 3rd supercomputer iteration specifically crafted for machine learning workloads. Like a master chef redesigning their entire kitchen to accommodate rapidly changing culinary techniques, Google found themselves needing to fundamentally rethink their hardware architecture as machine learning models evolved at breakneck speed, demanding new computational capabilities and interconnection strategies that previous generations simply couldn't provide. The most striking innovation in TPU v4 was its use of optical circuit switches, or OCSs, which dynamically reconfigure the interconnect topology between processing units in real time. Think of these switches as sophisticated railroad junction controllers that can instantly reroute trains along different tracks based on current traffic needs. Except here, they're routing data packets through optical pathways to optimize communication between thousands of TPU chips, allowing the system to adapt its internal network structure to match the specific requirements of whatever machine learning task is currently running.
These optical circuit switches brought remarkable practical benefits to the TPU v4 supercomputer, improving scale, availability, utilization, modularity, deployment flexibility, security, power consumption, and overall performance compared to traditional fixed interconnect approaches. The research team noted that users could even configure the system into a twisted 3D torus topology if their particular workload demanded such an arrangement. And remarkably, the entire optical switching infrastructure consumed less than 5% of the system's total cost and less than 3% of its power budget, while being significantly cheaper, more power efficient, and faster than comparable InfiniBand solutions. Beyond the optical networking breakthrough, each TPU v4 chip incorporated specialized processing units called sparse cores, compact data flow processors specifically designed to accelerate machine learning models that rely heavily on embeddings. These sparse cores operated like precision surgical instruments in an operating room, targeting very specific computational patterns with extraordinary efficiency, delivering 5x to 7x performance improvements for embedding heavy models while consuming only 5% of the chip's die area and 5% of its power consumption, making them remarkably cost-effective additions to the overall architecture. The performance improvements delivered by TPU v4 compared to its predecessor were substantial and measurable across multiple dimensions, like upgrading from a reliable family sedan to a high-performance sports car. TPU v4 outperforms TPU v3 by 2.1 times in raw computational throughput, while simultaneously improving performance per watt by an impressive 2.7 times, demonstrating that Google's engineers had successfully achieved both speed and efficiency gains, rather than trading one for the other, as often happens in processor design. The supercomputer configuration of TPU v4 scaled to 4,096 chips, representing a 4 times increase in size compared to TPU v3 supercomputers, and delivering approximately 10 times faster overall performance for large-scale machine learning tasks. This massive computational capacity, combined with the flexible optical circuit switching topology, proved particularly beneficial for training and running large language models, which require enormous amounts of parallel processing power and sophisticated communication patterns between processing units to handle their complex neural network architectures efficiently. When the research team compared TPU v4 performance against competing hardware architectures available at that time, the results demonstrated clear advantages across multiple metrics. Against similarly sized graph-core IPU BOE systems, TPU v4 delivered 4.3x to 4.5x faster performance, while comparisons with NVIDIA A100 systems showed TPU v4 running 1.2x to 1.7x faster, while simultaneously consuming 1.3x to 1.9x less power, like a marathon runner who not only finishes ahead of competitors, but does so while consuming less energy per mile. The environmental impact advantages of TPU v4 systems became particularly pronounced when deployed within Google Cloud's energy-optimized warehouse-scale computing infrastructure. The research revealed that TPU v4s operating in these carefully designed facilities consumed approximately 3 times less energy compared to contemporary, domain-specific architectures running in typical on-premise data centers, while producing roughly 20 times less CO2 equivalent emissions, demonstrating how hardware design and infrastructure optimization could work together synergistically. The TPU v4 project represented a comprehensive approach to addressing the rapidly evolving demands of machine learning workloads, combining innovations in optical networking, specialized processing units, and large-scale system architecture. Like a master architect designing a building that can be reconfigured for different purposes without major reconstruction, Google's team created a flexible, powerful platform that could adapt to changing computational requirements while delivering substantial improvements in performance, efficiency, and environmental impact compared to both their previous generation hardware and competing solutions available in 2023. And so, we reach the end of our gentle exploration through the intricate world of sovereign AI, from the nanoscale precision of chip manufacturing to the optical switches that route data through tomorrow's supercomputers. We've seen how nations' grand visions of AI independence must grapple with technical realities far more complex than the political rhetoric suggests. The true costs extend beyond mere spending into dependencies that span decades of development, specialized talent, and manufacturing capabilities controlled by few. Rest now with this understanding, knowing that behind every promise of AI sovereignty lies a web of challenges that few governments fully comprehend. Sleep peacefully, dear listener, as these ideas settle into their proper place in the larger story of our technological future.